Okay, so yesterday we did recursive rules and we did explicit rules finding terms, both the first few and a random term within. Today we're going to talk about how we sometimes need to find the sum of a set number of consecutive terms in an infinite sequence. When we do this, we use what's called our summation notation. I know it kind of rhymes. Our summation notation is going to look a little bit scary, but I don't know, it makes it much easier to find out what we're trying to do. So summation notation is a capital E. Oh, I know.
It's not an E.
It is.
That's a bent paperclip.
You're not wrong. Typically written as k equals 1 to m, with k equals 1 on the bottom and m on the top of some sequence A of k. So when I read the summation notation, this tells me that I'm taking the sum of terms 1 through m following this rule. So in order to take this sum, I first have to know those first m terms, and then I just need to add them together. So this would be the same as term 1, term plus term 2, plus term 3, plus all the way through term m, because that's what it told me I was adding together.
Wait, so what you say that is what did you say?
Okay, so this summation notation right here, the E tells me I'm taking the sum of terms 1 through m here will be a number, of the sequence that follows this A of k rule. So we'll give us the explicit rule here, which tells us how to find every single term that we need to find. Okay, so if I was writing this out expanded wise, this would be the sum of terms 1 through m from the sequence A of k. So there are a couple components to this that I like to point out. The first one is that the k value here is called the index of summation. In other words, it is the summation variable. It doesn't always have to be a k, but it sometimes is, or normally is actually. One and m here then indicate the smallest and the largest values of that summation variable. So what we're going to do next is we're actually going to practice finding the sum of the first m number of terms of a infinite sequence that follows a given rule. I'm glad that I was able to provide that reminder to you.
I kind of want to try one now. It's basically a vanilla shake with a bunch of syrup.
No, I don't like I share my face with.
Oh my gosh, it's so good. Can we take a class trip to Newtown?
That sounds fantastic. Okay, first example.
No, I'll use cash, so we'll have to find exact change. It's fine.
Absolutely not.
Everyone's really recording now, because I don't really like the shakes, but
Okay, example 1 is on the board. It asks us to find the sum of the rule that follows this summation notation from terms 1 through 4.
It's going to take a lot of space. Or should I? No. 3 lines.
It took me 4 seconds. So what does this mean exactly? If you see something like this.
the sum of term 1 through 4 with the pattern
So this is the rule for my sequence. I'm adding terms 1 through 4. So don't I first have to find terms 1 through 4 so I can add them together?
Yeah.
Yeah, so that's what I need to do first.
That's why I wrote what you said down, so you can just plug in with the sentence.
Okay, so my first term is gonna be A1. How do I find A1? Plug 1 in for the variable K, because K here is my summation variable. It could be an N, it could be a W, it could be a Z, it could be whatever they want it to be. Here it's a K. So I plug 1 in for K, and I get 1 squared times 1 minus 3, which comes out to equal what? -2. So my first term is -2. Now I need to find term 2. Again, what are we going to do with the 2? Plug it in for K. Then I'm going to do the same thing for terms 3 and 4. So you, I'm sure, can find them on your own.
Wait, so for these, do you want us to find 4 terms and then find the sum of?
And then add those 4 terms together.
Oh, so
Yes,
these
that's what we're doing.
all-
Yeah.
Add all 4 terms?
Yeah, add all 4 terms.
Whatever, like, not want us to add all terms.
No, summation literally means add all of these.
Oh.
Yeah. Okay, so term 1 is -2, term 2 is -4, term 3 is 0, and term 4 is 16. Did everybody else also get these term values? Now what am I going to do because it asks for the summation of these 4 terms? Add them all together. So my summation, I'm going to write it out formally.
Oh.
Oh, we do have to write that?
You do not, I am going to. That's not it. Okay.
Yeah.
I just wrote it out formally so we can see exactly what we were doing. What do I get when I add all those things together? 10. So the summation of the first 4 terms of this given sequence is 10.
The quick answers and
You do not necessarily have to, although it wouldn't be a bad idea to say the summation equals 10. Yeah, I would be okay with that, but you don't have to write out all of these after you already found them.
Are we ever gonna have to do like 1, 2, 3, 4, and then like 10 for this?
You can't skip. They have to be consecutive terms. But that's not saying I wouldn't ask you to find the sum of the first 50 terms in a sequence.
That's ridiculous.
That is a little bit excessive, but the point is the same. I can ask for as many as I want.
now I'm scared that that's gonna be.
Okay, let's go ahead and look at a way to shorten the way we talk about this, because it gets kind of exhausting to try and draw this E every single time I want to indicate a summation, right? That is exhausting. They end up kind of looking just funky. Like mine never turn out looking beautiful after a while. So they found a shortcut.
I really could have wrote literally anything to replace this.
Yeah.
But it's already making stuff up, so it doesn't really matter.
That's what that means.
Okay. Like you know what it is, Gabe.
This is what happens when we use
It's going like 5 minutes already.
So they found a shortcut here that is S of n. So anytime you see S of n, it literally means the sum of the first n terms of the given sequence. So in the previous example, we found the sum of the first 4 terms and it equaled 10, correct? So in this notation, we would say S of 4 equals 10. That's how you should write your answers.
Why did they even attempt the E if they could just?
Well, the E is the actual process of adding them. This is a notation for shortening what you did. This is the summarization. I found the sum of these number of terms. Does that make sense? So summation is the process. This notation is the summarization.
So you're gonna write all that out.
Correct. Yep. Are we all good with that?
Will it be given to us like that, or is that just how we write it?
That's how you write your answer.
Okay.
Yes. Or it'll say find S of 5 given this rule. It could be given to you like that as well. But it still means the same thing. So what this actually brings up is a whole new can of worms. Because now we have sums of so many terms in a sequence, right? But that also means that I can have a sequence of sums. It's like Inception happening right now. So let's just go ahead and write this out and I'll explain what I mean.
How'd your evaluation thingy go?
My observation 1-1.
Evaluation.
Really trusting that 7th period class.
Actually, he made a comment that they were very participative and involved in the lesson. I know, it was actually kind of nice.
It's also the class asks a bunch of questions. I guess it was a good class to be evaluated in.
You never know what's gonna happen, always on edge.
Right.
But it's really just kind of.
They probably figured that the class is too on topic. And she would need to learn how to keep on track. Even though we tried to get her off.
What happens if you like don't get a good evaluation?
I have no idea.
She's too good not to get in.
Well, this is also just my first time doing a dual credit class, so I really don't know. Hope never to find out.
They probably would like give her a warning, and then if they observe again and it's bad, then probably take her distance from the credit class.
That's a scary thought.
I feel like it's the same thing as driving. You know, they give you a warning, and then they're like, okay.
I feel like not all the time do they just give you a warning like that. I feel like it's
Okay, so back to the math.
based on.
So what I've written is that a real number S of n is called the nth partial sum. And then we have a sequence of S1, S2, S3, all the way through Sn and beyond, which is a sequence of partial sums. Okay, so I took all of these partial sums up to a certain term value, and those made up my S of n for that particular sequence. So S1 would simply be the sum of the first term. That's it. S2 then would be the sum of the first partial sum plus the next term, which would be A2. My third partial sum would be the sum of the previous sum, so S2 plus A3. So each partial sum takes the partial sum from before and adds the next term to it. So this is called the infinite sequence of partial sums. We can generalize this by saying that any partial sum S of n is equal to the previous partial sum plus term number n. Does that kind of make sense? Scroll up,
Where
like here.
would the A's be different each time, or would they be the same number?
Well, it's going to be whatever, like A1 is term 1 of whatever sequence we were looking at. A2 is term 2.
Oh, so they
term
would
3,
already
term 4.
given
Yeah,
us-
they would already be given to us, or we'd have the rule to find it. Yes.
Makes sense.
Does this kind of make sense? So we can take the partial sum of the first 5 terms, and that's just S of 5. But then we also have a sequence of how my sum increases over time, and that's what the sequence shows me. We're kind of okay with that. We're going to do an example where there's actual numbers, and you'll see a little bit better what's happening. Are we all done writing this? Okay. So the example we are going to look at,
It's gonna be long,
I don't think,
I'll be lying.
this particular example,
Yeah.
and it took me 7.
You can, yeah, you could probably squeeze it into 5.
But then we have one more set of, I don't know, kind of notes to write after this.
It's just that page.
So on this particular example in my notes, I also found the nth term, but we're not gonna have to do that here. We're just going to do the first 4 sequences, or the first 4 sequence sums. Okay, if you wanna look at the work for the nth sequence sum, that's okay, you can do that, but I'm not gonna require you to do that on your homework, so I'm not gonna require you to do that here in class. Okay? So it's gonna make it way easier. So my sequence is 1, 2, 3, and just keeps going, right? Infinitely in the positive direction. Which means that my sum 1 is going to equal what?
A1.
Just my first term, A1. And what is A1 here, Colin?
1.
1, look at that. So S1 would be 1, because it's just the sum of my first term. S2 then would equal sum 1 plus my second term, A2. Sum 1 was equal to 1. My second term is 2. So S2 here equals 3. Do we see how it's building off the previous sum? Yes. So then we just keep going. S3 would be S2 plus A3. Which gives me 6.
How do you know if it's a summation or just a,
Or just what?
finding the rule? Or how do you know?
It'll be really obvious in the question. Yeah. And then S4 would be S3
It doesn't give us 1.
plus A4. No, but we know what the 4th term is, don't we?
Oh, yeah.
What's the 4th term gonna be?
4.
4. Look at that.
You never know.
You're right, it didn't give us a rule, so that was technically an educated guess. But I'm pretty confident in that educated guess. Just gonna say it. Okay, so we found the first 4 summation sequence values. And then we're done, because that's all it asked for here. Which was basically just taking the sum of the first term, the sum of the first 2 terms, the sum of the first 3 terms, and the sum of the first 4 terms.
So this one we don't like that.
Nope, because I didn't want the sum of all the sums. I just wanted the sequence of the sums. Yes, ma'am. Oh, yes. Everybody okay with that? So what we're gonna do now is actually just write down some rules with some examples, and then we are finished.
You didn't find the end?
I said I wasn't going to on this because I'm not asking you to on your homework. But it is in my notes if you would like to look at it. Okay, so what we're gonna do now is write down all of the super fun stuff. I know.
I don't think anything super fun starts with the word begin.
You know what? You might be right.
I got a good chance.
What do you mean zero lines? So I know how to add that stuff.
So we're gonna start with the
Three.
sum of a constant. So the first theorem here is if I have the sum of terms 1 through n, where each term is some constant c. my summation then is going to be equal to the number of terms times the constant that I'm continuously adding to itself. So if I'm taking the summation of a constant value such as 4, my answer is going to be this number times whatever my constant is. Does that make sense? Because we're technically adding C n number of times. Everyone okay with that?
So if it's given to us like that, we just multiply it and see.
Correct. So we're going to do an example. And the example is the summation of terms 1 through 4 of the constant 7. This means I took 7 and I added it to itself 4 times, which is the same as 4 times 7, which gives me 28. So my summation for this would be 28.
This is like when you're not given like a pattern.
Right, because my pattern is that's just one continuous number. Does that make sense?
Yes.
Anybody confused by that?
What?
Okay, so Marissa, this was saying I added the first 4 terms and each of my term was 7. So I took 7 plus 7 plus 7 plus 7, which is the same as adding 7 4 times, which gave me 4 times 7, which is 28. Does that make any more sense? Okay, we'll talk about it. Everybody else, does that kind of make sense? Nadia?
Okay, so like with the k equals 1 at the bottom of the summation.
That just means we're starting at term 1.
Okay.
Yeah. Yep.
Will it ever like be a different number? other than
Usually
one?
not. Sometimes. Sometimes it could say like 5 to 10, but that's not very often.
Okay. But like it wouldn't be any different, just plugging in from 5 to 10.
Yep. Same process. Okay, so another example of this one still, because I think it's helpful, would be the summation from k equals 1 to 10 of pi.
That's gross.
What the heck?
What is pi?
3.34.
It's a number. It's a number that doesn't change. So it's still technically a constant, even though it doesn't look like one. Which means this rule still applies. My summation then of the first 10 terms, which is just pi added by itself 10 times, is going to be equal to what? 10 pi. And that would be it.
Oh, you're talking, okay.
So we just take the number up here and multiply it by the number that is our constant. Any questions on that? Okay, so then what if it's given to me a little bit differently? No idea. Let's say, for example,
But I have a feeling you're gonna tell me.
I have the summation from k equals m to n, again, still of some constant c. So this is what Nadia brought up. What if I don't start at term 1?
Yes.
It is whatever term I start at, but that's going to change the number of times that I'm adding this constant, correct?
You have to like subtract.
Oh, right there, say it again. You subtract m from n, equals, and then multiply your answer by the constant c. So we're finding the difference between the biggest number and the smallest number, and then multiplying that by c. Because if I start at 3 and go to 5, I technically only added c twice. Because to get from 3 to 5, I only had 2 numbers. Does that make sense? Okay, so we have to find the difference between these 2 numbers and then multiply that by whatever my constant was. Of course, we're going to do an example. Yes. Well, will what be negative? No, this one's always the bigger one. Always.
Do we ever start at a negative?
No, because each of these only work for positive term values. Okay, so the example we're going to do is from k equals 3 to 8 of the constant 9. So I'm finding the sum from terms 3 to 8, where each of my sequence values is 9. So this summation is going to be equal to 8 minus 3 times 9. 8 minus 3 is
5.
times
9.
9. I can't do math. Mine says, yeah, it says 54. That's definitely 45.
Just reverse it.
8 minus 3 is 5. 5 times 9 is 45. Are we all okay with that for the most part? Yes. Anybody confused? Okay, so now let's look at a couple other theorems. We are not going to do examples of these, but just know that they apply.
All of those E's that we just
How much
wrote
space
look
is it gonna
different
take?
on my paper. Every single one. Such a beat.
Oh,
That's funny.
Gotcha.
Yeah, I'm telling you, they never turn out the same.
No,
should just
one
buy
looks
a-
like almost a rectangle.
This.
Two of them look good, and the other ones are not
To
working.
change every single time.
One kind of looks like that anvil that, Westminster is.
Yeah.
$1 on Amazon, honestly. It's kind of bad.
Yeah.
Okay, so for this set of theorems, we're going to assume that we have two infinite sequences. They are denoted by A of 1 through infinity and B of 1 through infinity. So A is one sequence, B is one sequence. We're assuming that these are infinite sequences. And then for every term value greater than 1, so for every n greater than 1, we have 3 theorems that apply. The first theorem is if I have the summation from 1 to n of the sum of these two sequences, that is the same as taking the summation of each of the sequences individually and adding them together.
Whoa.
Our second theorem has the same idea, but with subtraction. So this is assuming that we are taking the summation of terms 1 through n of one sequence minus the other sequence. Again, this can be split into the summation of the first sequence minus the summation of the second sequence.
Just like Burger King. Yeah.
Okay. That's funny. Okay. These are just general rules that can follow, like if it asks you to find the sum of these two sequences for the first so many terms, you know how to do it. Okay, so there's one third one, and I think it's the easiest of all of them. And this third one says that if I'm taking the summation from terms 1 through n of a constant times a sequence, this is equal to the constant times the summation of that same sequence. So you would take the summation of the sequence and then multiply your answer by whatever that constant was. You can also put in parentheses.
You're
if
right,
that works
these
better.
either just go bowling every single time,
Oh,
I told you, it gets real bad.
like they're almost like connected at this point.
Yeah.
It's like an hourglass.
Yeah, it gets real bad over time. Okay, and then that is it for my notes. Yes, I will scroll up.
Wait, not that far though. I'm still on 2.
So the rest of class is homework time.